All right. Let's see. There. All right. Let's get started. Lecture 6 in Mechanics of Deformable Bodies. We are continuing our discussion today on axially loaded elements, and we are going to introduce what I think is really one of the analytical edges that this science gives us that statics did not, and that is the ability to handle problems that are indeterminate. We're going to handle two different types of indeterminacy today. That is problems with internal indeterminacy and problems with external indeterminacy. Now, I want to give everybody a heads up. Next Tuesday, I'm not going to be here, so I'm going to pre-record that lecture. If you understand what we're doing today with indeterminacy, then thermal stresses and strains are really easy to follow after that, because they're not, it's just a little bit of an added component, if you will, another Lego block on top of the contraption, and it's pretty straightforward. Really, I would argue if there's anything that's challenging, it's this one. It's indeterminacy. And so when I was looking through my schedule, I was like, which one do I want to do in person? I want to do this one in person, because this is the one that I think requires a little bit of attention. Okay. In terms of homework assignments, so homework 3 is still being graded, but I've got the solution posted. You all turned in homework 2.1 that was due today. How'd that go? Is that too bad? Hopefully. Okay, good. You're going to have homework 2.2 assigned today. It's going to be due Tuesday. It's going to have 2 problems on it. One internal indeterminacy, one external indeterminacy. So you'll kind of get where that's going with the lecture today. So with that, let's just get right into it. So I want to make sure that we're all sort of comfortable with the basic formulas. We're not going to add to this today. We will add to this with thermal stresses and strains, because we'll have another relationship to add, but it's not really anything that's too challenging. If we have a member that is subjected to a constant load, or a constant, or possesses a constant cross-sectional area, then the total elongation is pretty straightforward. We just compute PL over EA. P is the applied load, L is the member length, E is the elastic modulus or Young's modulus, and A is the cross-sectional area. We end up having to break out calculus whenever the load is variable or the cross-sectional area is variable. And again, as I've said before in this course, I don't want to just start throwing calculus out there for the sake of throwing calculus out. There needs to be a reason for it, in my opinion, and I think I showed you 2 examples where it's very realistic in class last time. The concept of member self-weight, that as the member gets longer, the member gets heavier, so that the load is variable as a function of length, and then the tapered bar. I mean, both of those examples are very real world. And finally, the other point is that if we take this expression, and I think this was clear in our first example, if we take this expression here and set the axial load and the cross-sectional area to constants, and we carry out that integral, we get this. Okay? If we set this to P, set this to a constant, factor everything out, what's the integral of dx from 0 to L? It's just L. So we get the same formula. Any questions about this? Okay. I touched a little bit on this in statics, but today we really need to talk about it because, well, if I would argue, one of the advantages of the concept of mechanics of materials, being able to relate applied loads to resulting deformations, is that we get some added advantages and some additional analytical tools to assess problems that possess static indeterminacy. I propose there are limits to what statics can do, and we're going to address some of those limits today. We're also going to look at how static indeterminacy presents itself in real-world engineering problems. And it presents itself really in 2 ways. We either have problems with internal indeterminacy, and problems with external indeterminacy. And so we're going to look at each of those. But first, I want to make sure that everybody's sort of on the same page with what I mean by indeterminacy. How many of y'all remember trusses in statics? Hopefully you did. We didn't do that. It wasn't all that long ago. So I want to take a look at this two-bar truss. Remember, what are our two methods for solving a truss? There was the method of sections and what? Method of joints. Now let's recap analytically and conceptually how the method of joints works. So you got a truss, right? It doesn't have to be this truss, it can be any truss, but you got a truss, you've got, first thing, you got a truss, you got loads on it, so the first thing you want to do is compute the support reactions. So you break out sum of forces, sum of moments, get your support reactions, and then you start applying the method of joints. So how does the method of joints work? Where do you start? Where did we start with method of joints in statics last semester? Like how did we begin that process? Like which joint can you start with? Exactly. We could not start with a joint that had 4 unknowns, 5 unknowns. We had to start with a joint that had 2 unknowns. And we could only progress throughout the truss with joints that had at most 2 unknowns. Does everybody remember that? Why? Why were we limited to 2 unknowns?
2 equations.
Exactly. When we're looking at the method of joints, we're dealing with a concurrent force system. And so for a 2-dimensional truss, we only have 2 equations of equilibrium at our disposal. We have the sum of forces in the x direction and the sum of forces in the y direction. So with that, let's take a look at this truss. So I have a 2-bar truss, and I have a load applied here at this joint here. And let's say I wanted to solve for the 2 unknown members, the unknown forces in the 2 members. I can write an equation for the sum of forces in the x direction, write an equation for the sum of forces in the y direction, 2 equations, 2 unknowns, and I can solve that using the principles of statics. Okay? I may have to break out the equation solver in my Casio FX115ES Plus or similar scientific calculator, but I can do it with just statics. Alright? Now, my problem is, what about this? What if I throw another bar in there? That's impossible if all you use is just statics. You cannot solve this problem using statics alone. This is a problem that is statically indeterminate. Okay? What that means is there's too many unknowns. This particular problem would be statically indeterminate to the 1st degree. That's sort of what we would say. What that means is there's one more unknown than can be handled using simple equations of equilibrium. Okay? And for you civil engineers out there, it is not that uncommon to deal with civil engineering structures that have multiple degrees of indeterminacy. I mean, just looking at a simple building frame, you could have static indeterminacy of 20, 30 degrees. It's not that uncommon. And in those scenarios, that's what software and whatnot is for. But for basic rudimentary analysis, a single degree of indeterminacy happens all the time. We're going to have a couple problems today that deals with that. Now, statics is not enough. You cannot solve for this system using just statics. What we learn in here, however, is what affords us to solve this. And basically, what we're using is what's called a compatibility relationship. In other words, that we relate the applied loads to the resulting deformations. And the idea is that those deformations, after the load is applied, must be compatible. We're going to deal with 2 different types of indeterminacy. Structures that exhibit external indeterminacy would be like that truss I just showed you. 1 too many members, or 1 too many support conditions, etc. There are also members that exhibit internal indeterminacy. An internal indeterminacy would be, for example, a composite member, a composite column. I have a reinforced concrete column, which means I have concrete and steel in the member. If I apply load, how much load goes to the concrete, how much load goes to the steel? That's an indeterminate problem. We're going to have a similar indeterminate problem here in a little bit. The main strategy, and we're going to handle it differently, we're going to use sort of different approaches, but the main strategy is to ensure that all the displacements are compatible. Okay? So, like for that truss, when I apply that load, it's going to deform. Each joint is going to move from its initial location. Here's the joint before you apply the load, here's the joint after you apply the load. So each member is going to deform. Some members might get shorter, some members might get longer. But the displacement of the joint and the displacement of the members has to coincide. They must be compatible. And it is that compatibility that we are going to utilize to assess some more complex problems. So I've got two problems we're going to do here in a little bit. This is a composite column problem. So I have a column that is 4 inches in diameter, and it is comprised of a 2-inch brass core surrounded by aluminum. Okay? So there's 2 different materials. And what I'm going to do is I'm going to apply a 9,000-pound load to this column. And the question is, how much load goes to the aluminum? How much load goes to the brass? It's not just half and half. You have to do the analysis. Okay? And then the other problem that we're going to deal with is this one right here. So this one, this is external indeterminacy. And in this scenario, I have one too many support conditions. So for example, I have 2.5 kips going upward, which means static equilibrium dictates I must have 2.5 kips going downward in order to achieve equilibrium. Well, how is that distributed? Is this 2 and this 1/2? Is this 1 1/4 and 1 1/4? How is that distributed? And the only way to really assess that is to use mechanics of materials. So these are going to be the 2 problems that we assess today. I'm going to go ahead and get us set up. Let me blow this up a little bit. That's a little better, isn't it? So, all right. Now, let's take a look at this. So, while everybody's writing this stuff down, I'll give you a minute, but let's take a look at some of the data. First off, we have a 1.5 foot long member. What's the first thing that you think we ought to do right now? We've got to convert to inches, right? So that 1.5 foot is going to be 18 inches. All right. We have a load here. Ooh, I have a little typo. That's supposed to be an exponent. Hold on. That's going to bug me. Does that go on the mistake counter?
Oh yeah, we'll let that go.
Man. I wouldn't turn that in. Okay. I'm going to get in trouble, man. That's what's going to happen.
No, it's all right.
Okay. So yeah, whoops. All right, I've got a composite column. The entire column is 4 inches in diameter, and it is a 2-inch diameter brass core that is surrounded by aluminum. So what we're going to do is draw a schematic of that to ensure that we get the areas and the dimensions and whatnot appropriate. One of the other things that's worth mentioning is that we've been given the material properties. Notice that we've been given the E for the aluminum and the E for the brass. So the brass is stiffer, if you will. It is a little bit of a stronger material. Okay. Now, what we're going to see, and I'm going to talk about this here in a little bit. One of the things that you find in analytics, if you will, is that stiffness tends to be a magnet. But when you have systems that are indeterminate and you look at the resulting stiffness, the elements that have the larger stiffness properties tend to absorb more of the load. If you ever get the chance, either you mechanicals or civils or whatnot, to do some maybe some more advanced finite element analysis or whatnot, if you're ever looking at some really large-scale finite element analyses, take a look at the stiffness properties and take a look at the resulting stresses. And stiffness kind of acts like a magnet. It kind of sucks in the load in a given system. The other thing that I do want to mention before we start this problem, because I know there's people writing stuff down, we were given the length of the member, but you're going to see here in a second how for this particular problem it doesn't matter. But you'll see why here in a second. Okay. Has everybody got this? Okay. So first off, let's get some properties. Okay. So okay, even the screen is cold. Okay. So we've got let's use some colors here. Okay, that's the best you're going to get out of it. Okay? So this right here is what we will call the brass sort of core of the column, and then this is the aluminum sheet. So by composite, I mean we have a column comprised of multiple materials that are acting together. Now what we were told is that the entire diameter, the outer diameter, was 4 inches, and we were told that the inner diameter was 2 inches. Okay? So what I want to do is I want to determine the area of the brass and the area of the aluminum. So somebody help me out. How would I determine the area of the brass? Let's start off with that. There you go. So I think I can do that one in my head because 2 squared is 4, 4 over 4 is 1, so that's just going to be pi, or 3.142 square inches. Now that's for the brass. What about the aluminum? So the aluminum, you remember, this is a pipe. Remember how we compute the area of a pipe? We take pi over 4 times d naught squared minus di squared. So we say I already wrote that. So what do we got?
9.42 square inches.
There you go, yeah. 16 minus 4 is 12. Over 4 is 3, so 3 pi. And 3 pi is, 9.425. Okay. All right, so far so good? Okay, now, what we're going to have to do is, so first off, the first thing I want to do is I want to look at static equilibrium. Equilibrium. So, let me scroll up a little bit. So, here's this column, and it's being subjected to a load of 9,000 pounds. Now, I want to break out my secret weapon of structural engineering, which is a samurai sword or a lightsaber if you happen to be a sci-fi fan. And I'm going to cut a section, and I'm going to look up. Okay? So if I cut a section and look up, what does it look like? Well, I've got my plate. I've got my load here. And what I've got is I've got sort of, this pipe, and I've got this pipe, right? And so this is where I cut a section. So So there's going to be some load here. We'll call it P brass. And then the aluminum is going to carry some load as well. Now the way I'm going to kind of draw this is I'm going to draw it kind of like that. We'll call it P aluminum. See, if I sum forces in the y direction, I get P aluminum plus P brass is 9,000 pounds. Or I tell you what, let's be formal about it. So that's everything going up minus 9,000 pounds going down is 0. So if I wanted to rearrange this equation a little bit, maybe what I'll do is I'll say, and I'm getting tired of writing like aluminum or brass out, so I'm going to say PA plus PB is 9,000 pounds. And this is sort of the crux of the problem. See, I propose that PA plus PB must be 9,000 pounds. But that's all statics tells me. That's all it tells me. This could be 6 and this could be 3. This could be 7 and this could be 2. This could be, theoretically, this could be 9,000 and this could be 0. I know that's not the case, but there's nothing in the realm of statics arms me with the ability to solve that. Okay? I don't have enough. So what I'm going to do is I'm going to call this equation 1. Okay? But I need another equation. Yes?
So why can't you convert the force applied at the beginning to a pressure over that area and then apply it to two areas?
Because, okay, that's fair, but it doesn't take into account the compatibility.
Them working together?
Yes, that's what it doesn't take into account. And so here's what I propose. I propose that the second expression must come from compatibility. And it is so simple in its execution. Let's keep this very basic. If I apply 9,000 pounds to the top of that column, what is the column going to do?
Squish a little bit.
It's going to squish a little bit, right? It's going to decrease in length. But what can you tell me about that decrease in length? Keep in mind, there's two materials. There's aluminum and brass. Would you agree that the aluminum is going to get shorter? Would you agree that the brass is going to get shorter? What can you tell me about those two shortenings?
They'll be the same.
Here is your second equation. This is what we're going to use to solve this problem. I propose that the shortening of the aluminum and the shortening of the brass are the same. And that's why pressure isn't enough, because it's not taking into account the stiffness properties of the aluminum and the brass. Now, I would argue that your proposal would be valid if the two components were made of the same material. But if they're made of the same material, then why are we looking at them differently? You know what I mean? So, with me so far? Okay. So, let's take a look at this second equation. So we'll call this solving. Let's expand equation 2. How do I compute the shortening, if you will, of the aluminum? Let me ask you a question. Are we dealing with constant loads and constant areas? So no need to break out calculus. So how do you compute the deformation of a bar, of an axial bar? What's the formula? Delta equals what? PL over EA. So we need PA, LA, EAA, right? Right? That would be the expansion, if you will, of the second equation. Now, I see a few people here going, wait a minute. Is there something that we could do right now to simplify this? What's that? Get rid of the L's. Why? Because they're the same. How long is the aluminum column? It's 18 inches. How long is the brass column? It's 18 inches. So LA equals LB, which equals 18 inches. So I'll say, note, so what's interesting is, what if I even didn't tell you how long the column is? What if I just didn't say it's a column of length L? Wouldn't matter. Which, by the way, there are some times in this class that that's going to happen, where you're going to get a parameter you don't need. So.
Yeah, that happened this week too.
What?
Yeah, you can factor out mass even though you're not given it.
Okay. Back to the land of stuff not moving. All right. Now what I'm going to do here is now I'm going to substitute in one of my equations. So we're going to substitute equation 1. What is PA plus PB? 9,000. So could I do this? Could I do that? Instead of PB, do 9,000 minus PA. Now let's take a look at this. 9,000 pounds. 9,000 pounds. Hold on. That's going to bug me. So let's see. Do I know the E's for each material? I was given that at the beginning. And here's the thing. I know they're aluminum. I know they're brass. If I didn't give you the E values, you could open up Appendix I in your textbook and look them up. That's one of the beauties of this science. We know the areas. We just computed those. The only thing that's unknown in this expression is PA. So all we got to do now is a little bit of algebra. So when I got two fractions set equal to each other, cross multiply. Right? So now what do? Let's distribute everything over on the right. Now let's move everything with our desired variable over to one side of the equation. Let's factor out the PA. And then let's divide. That's too much. So. Did I go too fast on the algebra, or is everybody okay with that? I tried to take it one step at a time. So here we cross multiplied. Here we distributed that out, isolated our unknowns, factored out, divided. Good? So now we just need to fill all this in, and I'm going to scroll down a little bit. Okay, so I'm going to leave everything in the units that were provided in the problem, so $3.142. Boom. So what does this come out to be? Hopefully everybody brought their Casio FX115 ES plus or similar scientific calculators. You know, it's funny when I say that there's a lot of people in the class that sort of like, they go like this, because they're like, I didn't bring my Casio FX115 ES. What'd you say? Oh, okay.
Don't worry about my GoPro.
They go, it's frozen. It's literally a block of ice. That might be a valid excuse today. What'd you get?
6,000.
6,000?
Yeah, I agree with,
Second, right?
Yeah, second.
Second. And 30. Okay, that's right. So PA is 6,000 pounds. And if PA is 6,000 pounds, what is PB? There you go. So come on. So what we're really interested in this problem, though, the problem is asking for the normal stress in each material. So just to make sure everybody's on the same page, how do I compute the normal stress in each material? Well, we've got the force, we've got the area, force over area, right? So interesting. So what is sigma A and sigma B? We'll say to like 1 decimal place. What about sigma A?
$636.74.
That's what I got.
Yeah, come on. All right.
Somewhere in there.
Okay, do me a favor. If there's an engineering design that like collapses and causes injuries, and you're getting deposed, somebody asks what the stresses are, don't say like, well, they're somewhere in there. you turn that in? All right, what about sigma b? I'm gonna get in trouble, man, that's all I'm saying.
Unless somebody snitches.
Sigma b,
Hey, don't tell me what to do.
954.9.
0.8.
But it's, I mean, it's all the same at this rate.
Yeah, it's so
Close enough.
All right, guys. All right. Now, listen. In all seriousness, like, I want to make sure that these concepts make sense. Like, because what I'm really trying to get at this problem is that at equation 1 last semester, we'd had to stop. There's nothing. We wouldn't have had the material or the tools necessary to solve this problem. This is what this science gives us. But beyond that, let's take a look at these answers. Now, I want to dig a little bit on this, and I want to see whether or not these answers make sense. Okay, so I got sigma A, which is 636.7 psi, and I got sigma B is 954.8 psi. So what that is telling me is that the brass is experiencing more axial stress than the aluminum. Now, is that desirable? I'm asking, what do you think? Okay, why? There you go, right? So this would be an example of a sound engineering design because the brass is a higher quality material. It can withstand more stress, right? While we are not looking at maximum stresses, a clue into this is to look at the E values. The E value for the brass is larger than the E value for the aluminum, which at a minimum means that brass is stiffer, right? So one thing one set of terms I'll start to use in here is the difference between strength and stiffness. Stiffness is the relationship between applied loads and resulting deformations. And so the way that you can characterize stiffness simply is looking at the E value. But strength is the maximum stress it can withstand before failure. So that's like looking at your sigma max or your sigma y or so on and so forth. And so I'm not saying that the brass, looking at these data, I'm not saying that the brass is stronger than the aluminum. I'm saying it's at least stiffer than the aluminum. Yes, sir.
So I got a question. So the only reason I can think of the aluminum around the brass would be to save on weight. Is there like another engineering reason why that would happen?
That's a great question. So that is one reason. Another reason is cost. Another reason, and this is probably more near and dear to the civils, could be for environmental protection. So let me give you an example. You go to the 3rd Avenue parking garage, right? Okay, the columns are made out of concrete, okay? But those are not just raw concrete columns, there is steel inside them, right? But if you were to samurai sword or lightsaber through the columns, okay, they would not look like this. It would not be like this, and then the rebars like right here. It wouldn't look like that, okay? Instead, the rebar is going to be inset some. So what it's actually going to look like is like this, okay? And there is some distance here between this and that. There is some prescribed distance, okay? We call that distance cover, okay? Now, the reason for that cover is for environmental protection. It's to prevent against water penetration and corrosion and so on and so forth. So, for example, you would have different cover requirements for a reinforced concrete column inside a building than you would, say, a pier for a bridge in Miami that's exposed to salt water. It's going to be a different deal. So maybe the aluminum is serving as an environmental protectant, right? We put coatings on alloys and polymers all day long to prevent against corrosion and thermal protection and abrasive environments. That's another very realistic reason for it. So money, environmental protection, you name it. So that's a great question, though. Any other questions? This is good stuff. I like this. Okay. Is it this one? Okay, let's look at this problem. So this problem is a little easier from the material perspective because we only have one material to deal with, okay? But the problem with this one is that we have an external indeterminacy. Now, I want to put a point of clarification on the problem because I think that some of you who are trying to be statics purists, if you will, might go to this support, let's say at B, and go, I remember that, that's a fixed support, right? And fixed supports in statics land had 3 reactions, right? A reaction in the x direction, a reaction in the y direction, and a moment reaction. Y'all remember that? Okay, and that is 100% true. But for the context of this problem, the only forces that are being applied are acting up and down. So from a statics perspective, we can reasonably say that any horizontal reactions are 0 and any moment reactions are 0 because there are no moments, there are no horizontal reactions. The only thing that we're dealing with are vertical reactions, okay? So I propose that there is a reaction at A and a reaction at B. And just as before, if I sum forces in the y direction, I'm going to get that RA plus RB is 2.5 kips. But that doesn't tell me how much RA is. That doesn't tell me how much RB is. So I still have sort of the same problem. But I am going to treat this problem a little bit differently. Okay? So, first off, let me give everybody a chance to write all this down because I want to make sure I have your attention on this. This analytical technique is a little bit, how can I put this? It's a little bit quirkier than the last one. I think the last one was pretty natural and pretty straightforward. But what we're going to do for this problem is a little different. So I want to make sure everybody is on the same page with this. So, okay. Let me ask you a question. So what we're going to do is we are going to again utilize compatibility relationships, okay? But with this problem, we have sort of a couple of different options, okay? So here's what I'm getting at. I have 2.5 kips going upwards. I need 2.5 kips going downward in order to maintain equilibrium. I propose that there's one additional reaction, or specifically one redundant reaction. I could delete RB from the equation altogether, from the problem altogether, and the problem is still statically in static equilibrium. I got one too many reactions that I really need. So I am going to treat one of those as a redundant. And what makes the problem maybe a little quirky is that I could do the problem treating either one as the redundant and still get the same answer. Let me ask you a simple question. So if this right here is equation 1, we need equation 2. Somebody help me out. What is the deflection at A?
RB minus the thing on the right, I can't read that.
No. The deflection. What is the deflection at A? When I apply load, so if I apply this 2.5 kip load, I propose that the bar might shrink or elongate or so on and so forth. I'm asking how much does point A move? Say it again?
0.
0. That's going to be my compatibility relationship. So for compatibility, I'm going to say that delta A is 0. And that's going to be my second equation. But how we actually apply that is a little different than what we did last time, okay? So I want y'all to pay attention to what I'm going to do here. And I want to be crystal clear. I flipped the coin. I could have very easily said that the deflection at B is 0. And I would ultimately get the same answer at the end of the day. On your homework assignment, I'm telling you which one I want you to treat as the redundant so that we all do it the same way. Okay? So I just want everybody to be aware of that. Okay. So let me show you the method of consistent deformations. So here's what the method of consistent deformations looks like. I have some bar, and let's say it's got a load right here, it's got, maybe a variable load right here, it's got a load right there, all sorts of different loads on it, okay? So what I'm going to do is I'm going to do two separate analyses, okay? So the first analysis, what I'm going to do is I'm going to delete one of those supports, okay? Doesn't matter which one, okay? And I propose that when I delete that support, that this point over here is going to deform some amount. We'll call it delta A. So I delete that support, the bar elongates, okay? And so I compute delta A. And let's say I get delta A is, 0.36 inches. I just made that up. What I then do is a completely separate analysis on this bar right here with no loads present, and I ask how much force do I need to apply to get it to deform 0.36 inches in the other direction, right? So the idea is that if I remove this support, it deforms 0.36 inches to the right. How much load is required to deform it 0.36 inches to the left? And whatever that load is, that is the reaction. Okay, does that make sense? Because the idea is that if I take this reaction and I put it there, the net displacement is 0. Everybody with me on that? So let's see how that works for this problem. So we remove the supported A. Here's the problem. We have a load right here of 2.5 kips. We were given at the beginning of the problem these lengths. This length is 36 inches. This length is 72 inches. Let's name these. Let's call this A, C, and B. We know what E and A are. So let me ask you a question. Looking at this problem, we have the axial force inside member AC, the axial force inside member BC. How much axial force do you think is inside member BC? Like if I cut a section, how much force is in this component? Like, let me ask it this way. What's this reaction right here? If I have 2.5 kips up, it's not a trick question, I promise. I'm not.
At least 12.
At least 12. 2.5 kips downward. So here's what I'm getting at. Would you agree that this component is experiencing 2.5 kips in tension. So how much is this experiencing? I promise it's not a trick question. All right, here's what I want you to do. How many of you have a pencil? I want you to grab one end and then grab the middle of it and yank it. How much force is this free end experiencing? You need a higher E value for your pencil. Now, hold on, watch my hand. Hand. I'm yanking. How much tensile force is in this part of the pencil? None.
Yes, sir. Let's go.
This is 0. Does that make sense? Here's my point. I propose that for this problem right here, the deflection at A is this plus this. And this part here goes to 0. That's what I'm getting at. Because for this particular problem, there's no axial load in that upper segment. So we have 2.5 kips. We have 72 inches. We have the E value for this problem. We were told at the beginning that E was what, 29,000? And I think we were told that A was 8 square inches. Is that what it said at the beginning? Yeah. So if you chug this out, and I'm going to tell you it's a pretty small number. I'll go ahead and write this one out for you. 0.000776 inches. It actually doesn't really matter what this number is because ultimately the net deflection is 0. But here's the overall point. Would you agree that if I removed that support at A, that point A is going to move up some? And it's going to move up this much. That make sense? So now what we need to do is we need to figure out how much load would cause it to move back down that much. With me so far? So now we're going to do a completely separate problem. We're going to do a completely separate analysis problem. So now we're going to apply the reaction at A. Now, I don't know how much that reaction is, so we'll call it RA. I have no idea how much it is. I don't know the magnitude. But I know the following. What is the total length right here? What's 36 plus 72? 108. So I know this is going to be RA. So let's take a look at this. We know my deflection is PL over EA. Well, what do I know? I know this is RA. I know this is 108 inches. I know this is 29,000 KSI. And I know this is 8 square inches. But what's that got to equal? It's got to equal this. Right? Because the idea is that this force system generates that much deformation. So I need to know what reaction will generate that much deformation in the opposite direction. Does that make sense? So what I'm going to do is rearrange this equation and solve for RA. So therefore, RA is, and all I'm going to do is flip and multiply. So 29,008 on the top, 108 on the bottom. So what is RA? There you go. 1.67 kips going down. Do I have a second on that? Alright, so that's right. So now what we can do is we can go back to the original problem. My goodness, this thing keeps popping up. I'll have to change the setting on this at some point. So now, if we go back to the original problem, so here's the original problem. What do we got? We've got and now we know RA is 1.67 kips. How do we determine what RB is?
So the force is in the y direction.
And we already did that, right? So we know that this plus this has to equal 2.5 kips. So what's 2.5 minus 1.67? What is it? 0.83? You want me to show you something kind of slick? Watch this.
Yeah.
So, would you agree, okay, so this is point A, this is point C, this is point B. Remember how I said that this is the method of consistent deformations? Watch this. Would you agree that member AC is experiencing what? 1.67 kips in compression? Would that be right? Would you agree that member BC is experiencing 0.83 kips in tension? Would you agree with that? I mean, if I cut a section here and look down, this part's getting yanked on, this part's getting pushed, right? I mean, imagine if I had a yardstick stuck between two walls and I grabbed one end and pulled it, right? This end's going to be in tension, this end's going to be in compression, right? And the amounts are just equal to the reactions. What do you think? You with me so far? Would you agree?
Some ratios for us.
Would you agree with that? So what I want to do is I want to determine how much this point moves. See, I propose that the deflection here and the deflection here are zero. But if I take this point and yank it, that point's going to deform. How much does it deform? Well, let's take a look at this bar. How much does this bar deform? Well, we know that E is 29,000 KSI and A is 8 square inches. Somebody help me out. What is that? So that times this divided by EA. are we getting?
Is it 2.59 times 10 to the negative 4?
That's not what I got.
That's what we
Oh, it is what you got?
Yep.
Okay, alright, I could have had a typo. Alright, what'd you get?
2.59 times 10 to the negative 4.
What about this? The question is, are you getting the same thing?
Should be.
Oh, I see what I did. You're right, I see what I did. Yeah, you're 100% right. Yeah, I see what I did. What are you getting for this second part?
2.58 times 10 to the negative 4.
You know, what did I say this method was called? The method of consistent deformations. It's almost as if the deformations are consistent. Marker drop. Oh, that's right. I'm going to keep the marker up. Okay, so the only difference that we're getting is the difference in rounding. See, what this is saying is that the reactions that we have computed, see, here's my point. This part of the bar is going to compress. It's going to get shorter. But this part of the bar is going to get longer. But the amount of deformations that we get in this bar has got to equal the amount of deformations that we get in this bar, because the deformation here has to be consistent. So my question for you is, what is the deformation at C? Well, let's just keep it simple. If I yank on this in this fashion, is point C going to move up or is it going to move down? Up. And how much is it going to go move up? Right there. There's your deformation. So what is the deformation at C? Or hold on, let's use lowercase l. I'm going to use 5.9. Oh, and by the way, let's do another box answer.
You're still missing your given parameters chart at the beginning.
You also that's minus 25.
It's actually more of a rectangle.
It's about minus 30.
Where were the parameters at?
This desk doesn't allow me, I can't crawl under this desk. Oh, goodness. Okay, so, all right, let me ask you a question. Let me stop for a second. Does anybody have any questions about this? Does this idea make sense? This concept of indeterminacy and how mechanics of materials gives us those tools necessary to handle indeterminate situations, both indeterminate situations that present themselves both internally and externally. Does that make sense? Okay, so all we're going to do in the next lecture is add one more parameter, okay? And here's the parameter. The parameter is, what if I took this bar and heat it up? Okay? When I heat things up, they expand. When I cool things down, they contract, right? So I don't need to explain to the people in the class like why we need to handle thermal stresses and strains. We design engineering systems that are not only subjected to mechanical loads, but thermal loads as well, right? You mechanical engineers are big fans of that stuff. Although in civil engineering land, we have to deal with thermal loads as well. How many bridges out in the state of West Virginia right now do you think are experiencing, single-digit temperatures this morning, and in the summer experiencing triple-digit temperatures?
Most of them.
Yeah. So do you think that bridges are experiencing thermal expansion and contraction?
Yes.
There you go, right? So if you think that thermal expansion and contraction only applies to the mechanical engineers, you're dead wrong. Now, I'm gonna highlight a little bit of this today because I want everybody to kind of understand how we do this. So I am skipping ahead a little bit, but I want the lecture that we pre-record to make a lot of sense. So the way that we handle thermal effects is we basically, it's really simple. What we define is we basically say for every change, for every degree in temperature change, we get an additional amount or a reduced amount of axial strain. So basically we say, okay, if I have an element that's subjected to a 50-degree change in temperature, I take 50 degrees, multiply it by a coefficient of thermal expansion, and that coefficient of thermal expansion will basically tell me how much strain I get per degree change in temperature, and that tells me the axial strain I get. Now, alpha is a material property. It is a material property just like E is, or the yield stress. So it's just a lookup, right? And it has units of like 1 per degree Celsius or 1 per degree Fahrenheit. One interesting tidbit for you civil engineers, steel and concrete have wildly different mechanical properties. They have different Young's moduli, they have different maximum stresses, etc. But one thing that's kind of interesting is that steel and concrete have very similar alpha values. So if you have a bridge out in West Virginia that's experiencing single-digit temperatures today, that's experiencing triple-degree temperatures in the summer, it's obviously going to expand and contract, but the steel is not going to expand at a significantly different rate than the concrete is. So you don't have like the rebar getting longer at a different rate than the concrete is, because if it is, you have rebar inside the beam that would be causing cracking because it's expanding or contracting at a different rate than the concrete is, and that actually doesn't happen. The alpha values for steel and concrete are serendipitously very, very similar. So I know that's an interesting tidbit for you civil engineers, but honestly, for the mechanical engineers in the room, if you have a system that's going to be comprised of multiple materials, and that system is going to be subjected to thermal loads, it might be advantageous to look at alpha values and see, am I selecting materials that have common or comparable alpha values so I don't get differential displacements under thermal effects. So just something to think about because that happens, you know. What we're going to do on our pre-recorded lecture is basically account for thermal stresses and strains. And so all we're doing is taking the expression that we had done before and just adding, well, what if the temperature varies? What if the strain varies? You know, so on and so forth. And so we have a couple problems. One where we're going to heat a bar up, we're going to cool a bar and see what happens to the resulting stresses and strains and whatnot. And then I have a bar that's subjected to not only a mechanical load but a thermal load, and we're going to look at the resulting stresses and deformations, etc. I don't think that if you understand what we've done in the past couple lectures, this is not going to be all that difficult. It's just going to be a little bit more. So yeah. Any questions? Yes.
Can we go back? Can you pull up the example that we just did again?
The example we just did, yes. Hold on. Where am I going?
Go down just a little bit. A little bit more, right there. What is stopping us from setting up a system of equations where we know that RA plus RB equals 2.5 and then say that PAC times LAC equals PBC times LBC?
That actually nothing, but I think that this approach is a little bit more. I think it's a little bit more direct and results in less computations. I don't think you're going to have, like, what I'm trying to avoid is a bunch of matrix math and, like, actual 2 equations, 2 unknowns type scenarios. But you could do that, you know. I think that's a little cleaner. One of the other things I want to say is I am presenting this in a fashion that I think is best done by hand. If we were trying to present this in a fashion that would best be done by a computer, we would be in the realm of finite elements. And that's basically what a finite element analysis does. How many of you have ever heard of finite elements or ANSYS or Abacus or any of that stuff? Okay, you've probably seen it in NX and whatnot. This is basically what those software packages do, is they write stiffness matrices for each of the elements that are discretized by the software. It assembles them, and then it turns it into a series of linear equations, solves it to get the displacements, and then back substitutes those displacements to get stresses and strains and whatnot. And so what I'm saying is that there's actually a much more general way of doing this stuff all together, but it involves some much more advanced math, some energy method stuff, and right now we're crawling. That's like walking and running stuff. So but I can talk about that stuff all day. Part of my PhD was developing finite element analysis routines for given bridge systems and whatnot. So don't get me started. You'll be here. Everybody's like, no, we might miss our next class. All right, everybody, is that all we got?
It's on time today.
You gotta get there early.
I get it, because none of us were there.
I'm stopping the recording.
Mas lang yan, sir.